Hi everyone. I had a request come in to go over the Chapter 5 homework problems. The first thing I want to address is some people felt like it's not the same as what we went over in lecture, but I want to assure you that it is. It's all based off of everything in the lecture, maybe slightly different than the example problems we went over, but everything needed to solve these questions is in your book and covered in lecture. Okay, so let's go ahead and look at these problems. Your first one tells you that according to the nutritional information on a package of jasmine rice, each serving contains 160 calories of energy. If 1.21 grams of jasmine rice is burned in a bomb calorimeter initially at 25.2 degrees Celsius and having a heat capacity of 8.73 times 10 to the third power joules per degree Celsius, what will be the final temperature of the calorimeter when the reaction is complete? So I think a good way to start with this problem is to write down what you're given. And one thing we're told is that one serving is a quarter cup, or we're just going to go ahead and say it's 45.0 grams, and that it contains 160 calories, or kcal is what I'm going to use here, just so I don't get little calories and big calories mixed up. We're also told our mass of our rice is 1.21 grams. And the initial temperature of the calorimeter is equal to 25.2 degrees Celsius. And then we're also told the heat capacity, not specific heat, but the heat capacity, so the big C of the calorimeter, is equal to 8.73 times 10 to the third joules per degree Celsius. So, one thing that we know is that heat capacity, again, not specific heat, we learned about heat capacity first, is equal to Q over delta T. So if we're looking at this for the calorimeter, okay, so that means it's equal to Q, or the heat that the calorimeter gained, divided by its final temperature minus its initial temperature. Now we need to find this Q for this calorimeter. And one thing that we also know is that the Q of the rice that it lost is equal to the negative Q of the calorimeter. Because remember, the heat that one thing loses is equal to the heat that the other gains, or Q cal is equal to negative Q rice. Either way. But we're focusing on the absolute value here. So let's go ahead and get this Q rice. And we can get this right away because we're told we have 1.21 grams. And we know that there's 45 grams in one serving, and one serving has 160 kcals of energy. So now we've gotten to kcals of energy, but we need our units in terms of joules because our heat capacity was given as joules. So we need to go ahead and continue to convert from calories to joules. And we can start by saying, okay, there's 1,000 little calories per 1 kcal, because the conversion that's given in your book is from calories to joules. Don't forget the back of your book in the appendix, I think it's appendix B or C, has conversion factors for you. And there's 4.184 joules for every 1 little calorie. So we can see our units all cancel out, leaving us with joules. And this comes to be 18,000 joules. So now we have a Q, and we are looking for T final. We know T initial. So just kind of solving for T final and rearranging, we know that delta T is going to be equal to Q over C. So Q over C is equal to T final minus T initial. So T final is equal to Q over C plus T initial. So the other thing we can say is Q rice is equal to negative Q cal, or Qcal is equal to negative Q rice. So we could say that the Q of the rice, that it's 18,000 joules lost. So then the heat of the calorimeter is equal to 18,000 joules gained, or positive 18,000. It really doesn't matter overall. But we just want to make sure that we are being careful with our signs. And since we are focusing on the calorimeter increasing in temperature, it makes sense that it's going to have an increase in heat, and so that has a positive Q. Okay, so we know Q, we know C, we know T initial, so our last step is to plug and chug. So we're going to put in 18,000 joules for Q divided by C, 8.73 times 10 to the third joules per degree Celsius. So we can see our joules cancel right there. Plus T initial, 25.2 degrees Celsius. This degree Celsius is going to end up coming up top when you have 1 over Celsius, or joules over Celsius. So that's how those units end up working out. And you end up getting 27.3 degrees Celsius for our final temperature. So it only goes up just over 2 degrees. So that is number 1. Number 2, calculate the amount of heat released, the absolute value, when 0.500 kilograms of liquid ethanol is burned in excess oxygen to make carbon dioxide and liquid water. The enthalpies of formation and reactants are that. So we're given a mass of ethanol, I'm going to write this as ETOH, of 0.500 kilograms. But what we need to do before we can do anything is we need the reaction. So we're told liquid ethanol, and its formula is given there. So this is C2H5OH, and we are burning it with excess oxygen, so O2 gas, and this reacts to form carbon dioxide and water. So this is a combustion reaction. Oops, not liquid, gaseous water. So we have the reaction, but we need to balance it. And there is a way to do this kind of quickly when it comes to balancing combustion reactions. The first step is you take the subscript of carbon that's on our hydrocarbon, and it's the same for CO2. So we're balancing carbon first. So now we have 2 carbon on each side. The next thing is you look at the number of hydrogen you have. So we have 6 hydrogen in our hydrocarbon. Divide that by 2. And that's what goes in front of water, so 3. So now we have 6 hydrogen on either side because 3 H2Os. And then the last part is you're going to add up all your oxygens on the product side now that you have your coefficients. So we have 4 oxygens from CO2, 3 oxygens from water, so we have 7. And then go back to your reactant side, look at your hydrocarbon. Normally, if it's just a regular hydrocarbon, it's just carbon and hydrogen, you don't need to do this step. But here, since we have ethanol, so we have an alcohol on it, there is an oxygen here. So there's 1 oxygen, so we need to subtract 1. That gives us 6. Take that number, divide it by 2. That's what goes in front of O2. So there you go. So now we have our balanced reaction. I don't know if that makes sense, but if it doesn't make sense, just balance it the old-fashioned way, but do oxygen last. Do carbon first, then hydrogen, then oxygen to balance these. Okay, so you have your balanced reaction, and then we're also given delta H's. So these are all enthalpies that they gave us. And one thing we know is that the delta H of a reaction is equal to the sum of each of the products multiplied times their coefficient minus the sum of the reactants, or your delta H's. So on our product side, we have 2 times delta H of CO2 plus 3 times delta H of water minus 1 times delta H of ethanol plus 3 times the delta H of oxygen. So now we can fill in our numbers. So we have 2 delta H of CO2 is negative 393.51 plus 3 times delta H of water is negative 285.83. Everything is in kilojoules per mole, so we can write that in at the end if you want, but just make sure that your units are okay. Minus 1 times delta H of ethanol is negative 276.0 plus 3 times delta H of oxygen is 0. So then this gives us negative 787.02 plus negative 857.49 minus negative 276.0. Minus negative is a plus. So this adds up to negative 1,368.51 kilojoules per mole. So now we know the delta H of the reaction per mole, and so now we want to get the amount of heat released for 0.5 kilograms of ethanol that's reacting. So we know how much it would be for every mole reacted. Now we need to know how much we actually reacted here. So we have 0.500 kilograms of ethanol. And the first thing we should do is switch this to grams. So we have 1,000 grams per 1 kilogram. And then a safe bet here, since our energy is in kilojoules per mole, then we need to have moles, so we know how many moles we actually are releasing energy from. So kilograms cancel. So we have grams on top, that means we want moles on top and grams on bottom. So we're using good old molar mass here, 46.07 grams per mole for ethanol. And then we can use our delta H also as a conversion factor, 1,368.51 kilojoules for every 1 mole. Moles cancel, we're left with kilojoules, and you get 14,853 kilojoules. But ChemVantage is being a little picky on this problem, wanting sig figs. And for some reason they want 3 sig figs, so if you're having issues, it's probably a significant figures. So this becomes 1.49 times 10 to the 4th kilojoules. So yeah, check your significant figures if this one was an issue, if it wasn't giving you credit. Oops. Okay, number 3, a soft drink, 330 milliliters of mostly water, initially at 10 degrees Celsius, is cooled by adding 151 grams of ice cubes at 0 degrees Celsius. What mass of ice remains when the temperature of the drink reaches equilibrium? The enthalpy of fusion of water is 6.007 kilojoules per mole. The density is 1 gram per milliliter. Assume the specific heat capacity of water is constant and equal to 4.184 joules per gram per Kelvin. I highly recommend you rewrite this as joules per gram per degree Celsius. Because, well, technically it's basically the same, but because the spacing between 1 Kelvin and 1 degree Celsius is the same. But the Kelvin can kind of mess with things, so you actually want this to say degrees Celsius. I personally submitted a comment to ChemVantage about this. Okay, so let's kind of organize what we know. We have a V1 of equal to 330 milliliters. And let's go ahead and just change this over to grams right away, since we were given density of water, 1.0 grams per 1 milliliter. So we have 330 grams. And then we're also given a mass of ice of 151 grams. We are told that the initial temperature, T0 of the ice, is 0 degrees Celsius. And that T final of the ice is also equal to T final of the soda, or water, however you want to say it, and that is 0 degrees Celsius. So we're putting in enough ice so that there's still some left over, but we're cooling the drink down to 0 degrees Celsius. Okay, and we're told delta H fusion is equal to 6.007 kilojoules per mole. And specific heat of water, which we're using for both ice and liquid water, is 4.184 joules per gram degrees Celsius. So we know that the heat lost by the soda is equal to the negative heat that is gained by the ice. So let's go ahead and calculate the amount of heat that the soda lost. So we have 10 degrees Celsius. That was the other thing, as we were told T1 for the soda is 10 degrees Celsius. And we know that it has a specific heat of 4.184 joules for every 1 gram times 1 degree Celsius. So gets rid of our degree Celsius. And we also know we have 330 grams that we converted earlier, so that gets rid of the grams here. So this gives us 13,807.2 joules. So that's how much heat is lost by the soda. So this is also equal to the amount gained by the ice. Okay, or if we want, we could also put this as negative Q lost soda. Okay, so then that means if this is, then that means this is negative Q gain. So Q gain by the ice is equal to 13,807.2 joules positive. It really doesn't matter with our signs. We can even use absolute value here. Okay, so now we can use this to find out how much ice melted using that and the heat of fusion. Oops. So we have 13,807.2 joules. And the heat of fusion tells us we have 1 mole of ice for every 6.007 kilojoules of it. And we also know that there's 1 kilojoule per 1,000 joules, so that way our units work out here. And then that'll give us moles of ice, or moles of solid water. And then we need to get to grams though, because we want to know the grams that melted, so we're going to use molar mass. And there's 18.02 grams of water for every 1 mole. And so this calculates out to be 41.42 grams of ice that melted. So our mass of ice remaining is equal to what we started with, 151 grams minus 41.42 grams. We have 110 grams of ice remaining. So this was more of an out-of-the-box question to kind of work your minds a little bit. You had to use Q loss equals Q gain, but then you had to transform that heat into something else as well. Okay, number 4. When 10 milliliters of water at 29 degrees Celsius is combined with 13 milliliters of water at 90 degrees Celsius, what is the final temperature of the water? The specific heat is 4.184 joules per gram. Again, change that to degrees Celsius, and its density is 1 gram per milliliter. So let's start by just kind of summarizing what we know. We know the specific heat of water is 4.184 joules per gram degrees Celsius. we know the density of water. I'm not going to bother writing that down though. We also have some volumes here. So V1 is going to be this 10 milliliters of water, and we can go ahead and just immediately make that into grams. 1.0 grams per 1 milliliter, so we have 10 grams of water. And it is also at an initial temperature, so T1 of 29.0 degrees Celsius, or this is T1 initial. And then we have some V2, some other bit of water, 13.0 milliliters. Again, make this into grams, 1.0 gram per 1 milliliter. So we have 13 grams here. And some T2 initial is 90.0 degrees Celsius. And we want the final temperature. So we know that the Q gained by one is equal to the negative Q lost of the other. So we're going to be setting these equal to each other. And we also know that Q is equal to MC delta T. So that means we're going to have M1C1 delta T1 equals M2C2 delta T2. But they're both water, they both have the same specific heat, so those specific heats are going to cancel out. We don't even need it here. So then we have that M1 times delta T1, which is going to be T final minus T1 initial. So remember, they're both going to have the same final temperature. It's equal to M2 times T final, equal to negative, don't forget that negative sign, times T final minus T2 initial. So we need to solve for T final. So we can divide both sides by M1. I like to do things in terms of variables to start. That equals negative M2 over M1 times T final minus T2 initial. Just kind of rewrite this in a minute. Negative M2 over M1 times T final plus now M2 over M1 T2 initial. So just putting everything on the same side, we get T final plus M2 over M1 times T final is equal to M2 over M1 times T2 initial plus T1 initial. So then that gives us M2, which is 13.0 divided by 10.0 times T2 initial is 90 degrees plus T1 initial, which is 29 degrees. So this is 146. So then T final, we don't know what T final is, so we have T final plus M2 over M1, which is 13 over 10, which is 1.3. So then this comes out to be 2.3 times T final is equal to 146. Divide both sides by 2.3, and you get that T final is equal to 63.5 degrees Celsius. So this was a matter of Q lost equals negative Q gain and setting them equal to each other and solving for T final. Number 5 is a little tricky with the setup, but once you get that, you're good to go. So we want to know how much heat is transferred from a 4.80 gram gold nugget with that specific heat initially at 51.7 degrees Celsius when it's dropped into 5 kilograms of water at 25 degrees Celsius. So there's a hint that they do give you here if you need it, and it's that the mass of your water is so much bigger than the mass of your gold that your T final is going to equal the same as your T initial of your water. So it's not enough to do anything to change that temperature of the water. So that 25 degrees Celsius is going to be the final temperature of your gold and your water. It's not going to change. So now we can calculate the heat from the gold. It goes MC delta T. So we have 4.80 grams times specific heat, 0.129 joules per gram degrees Celsius, grams, times delta T. So we have 25 degrees Celsius minus initially 51.7 degrees Celsius, so that you can see where the degrees Celsius goes away, and you end up getting negative 16.55 joules. But we want to go ahead and take the absolute value of it, because when we're saying it's this much heat transferred, saying transferred kind of makes up for that negative sign. So then that gives us 16.55 joules. So this was a setup, tricky setup one. Okay, number 6. The gas inside a flexible container is allowed to expand against a constant external pressure of 1.8 bar until the volume increases from 2.40 to 6.70 liters. Calculate the amount of work done on the system. And I have a feeling this is the one that people thought was not related to the chapter, but we did talk about work a little bit. And work is equal to negative pressure times delta V. And there are 2 ways you can do this. Both will get you the same answer. The first is to use SI units. Okay, and so SI units, let's see, I guess I'll just kind of do it. Are that pressure is in pascals and volume is in cubic meters. So we need to take all of our units and transform them. So then the pressure equals 1.80 bar. And when you look in your appendix for the conversion factor, there are 10 to the 5th pascals for every 1 bar. So this gets you 1.80 times 10 to the 5th pascals. For our volumes, our initial volume is 2.40 liters. And we need this in cubic meters. The back of your book tells you it's 0.001 cubic meters per 1 liter. So this is 0.0024 cubic meters. Do this for our final volume also, 6.70 liters. You could also do delta V and then transform that, but it doesn't matter. You'll get the same thing either way. And this is 0.0067 cubic meters. So delta V then is equal to V final minus V initial. And that is 0.0043 cubic meters. And a pascal times meters cubed is the same thing as a joule. So then our work equals negative P, so negative 1.80 times 10 to the 5th pascals times delta V, 0.0043 meters cubed. This gets you negative 774 joules. The other way is when you look in the back of your book, you are told that there's 101.325 joules for every 1 liter times ATM. And so if you look at that liter ATM, we already have liters from our volume, but ATM we can get from bar. So we start by doing our pressure. So 1.80 bar. Now in general 1 bar is about 1 ATM, but if you want to be more precise, you do it this way. Your book doesn't give you an exact bar to ATM, but you can go from bars to pascals, and then from pascals to ATM. 101.325 pascals, so those go away, and so you get 1.78 ATM. Pretty much 1.8 bar. So now we have work equals negative P delta V. So negative P 1.78 ATM times our delta V, which is 6.70 liters minus 2.40 liters. So this is negative 1.78 ATM times 4.3 liters. And so this is negative 7.654 liter times ATM. So our last step is now to convert this liter ATMs into joules. So we have 7.654 liter ATM, and then we use the conversion factor we found earlier, 101.325 joules for every 1 liter times ATM. So then this gets you, don't forget that negative 776 joules. So about the same. That difference is just because of rounding error. So either way will get you the right answer. All right, number 7. To measure the caloric content of a new breakfast bar, you burn a 2.80 gram sample in a calibrated bomb calorimeter. During the burn, the temperature of the calorimeter rises from 25.4 degrees Celsius to 28 degrees Celsius. If the serving size is 42 grams, how many calories are contained in each serving? Okay, so let's go ahead and just kind of summarize what we know. We know the mass for our bar is equal to 2.80 grams. And we also know that 1 serving is equal to 42 grams. Oh. Whoopsie, and that's supposed to say number 8. Let me just erase that and go back. Somehow I changed that and didn't even realize it. All right, let's try it again. The mass of our bar is 2.80 grams. 1 serving is equal to 42 grams. We know that the heat capacity, big C, of our calorimeter is equal to 8.40 kilojoules per 1 degree Celsius. And let's see, we have a final temperature of our calorimeter of 28 degrees Celsius, and its initial temperature was 25.4 degrees Celsius. So then delta T is, let's see, 0.6, 2.6 degrees Celsius. Let's write that a little nicer. There. Okay. So we have our delta T now, and we also know that the negative Q calorimeter is equal to Q of our bar. So Q, that would be negative C delta T, which is negative 8.40 kilojoules per 1 degree Celsius, times delta T, 2.6 degrees Celsius. And so this gets us negative 21.84 kilojoules. So now we know that the bar, for that mass, at 2.80 grams, is going to burn 21.84 kilojoules. So we have 21.84 kilojoules for every 2.80 grams. So now we have a new conversion factor. So now let's go with our 42 grams. That's in 1 serving. You don't really need to write 1 serving, but it's more of a visual thing for me. And we know that there are 21.84 kilojoules burned or given off for every 2.80 grams of breakfast bar. And we also know there's 1,000 joules per 1 kilojoule. And this would give our answer in terms of joules, but we want to know calories, big C calories, or kcals. So now we need to go ahead and convert to calories. And there's 1 calorie for every 4.184 joules, and 1 kcal for every 1,000 little calories. So you can see our units canceling out, and we get 78.3 kcal, or big C calories. I don't know why that says 2, but I will correct this to be number 8. So if you're watching this and you download the PDF, it should already say 8. Anyway, number 8, an iron rod initially at 27.1 degrees Celsius comes into thermal contact with an identical rod at 48.1 degrees Celsius. What will be the final temperature of both rods at equilibrium? So I'm going to first start by writing that the Q gained of one is equal to the negative Q lost of the other. And let's just kind of start putting in MC delta T. So we have M1 C1 delta T1 is equal to M2 C2 delta T2. But what do we know? We know they're identical. That means that their masses are going to be the same. And it also means that so are their specific heats. So those cancel out. So delta T1 is equal to delta T2. And we know, or negative delta T2, sorry. And we also know that T final for 1 is going to be equal to T final for 2. Oops. So we're just going to go ahead and call it T final without a number, just TF. So then, I keep pushing things on my laptop. Sorry, guys. Well, I guess it just wants me to fix the 8 while I'm still doing this. Okay. Anyway, T final minus T1 initial is equal to negative T final minus T2 initial. If you don't put that negative sign, you're going to be thinking that you're trying to say that the two initial temperatures are the same. So you can just rewrite this as negative TF plus T2 initial. So let's go ahead and put the T finals on one side. That gives us 2TF. And put the initials on one side is equal to T2 initial plus T1 initial. And T2 initial is 48.1 degrees Celsius plus T1, 27.1 degrees Celsius. So go, and then divide both sides by 2, and that gives us T final. So T final equals T2 initial plus T1 initial over 2, which is 48.1 degrees Celsius plus 27.1 over 2. And so this is 37.6 degrees Celsius. So it ended up being an average of the two temperatures. So this one was probably a little quicker and simpler, but I think the real challenge here was the actual setup. Being able to recognize that they're identical, which means their masses and their specific heats are going to be the same. All right, I hope this answers your questions. Of course, if you need more help, please don't hesitate to ask. And I hope you guys are doing well. I will talk to you soon.